In this problem, we're asked to find the maximum weight the flower pot can be so that neither cable exceeds its maximum allowable tension of 50 pounds. So again, we want to find what I'm going to call W max, and I will be in the free body diagram denoting what W is. That's again the weight of the flower pot. And we'll be given, well, the figure, and what I'll call T max is 50 pounds. Okay, so we are going to need to draw a free body diagram for this because we are in static equilibrium, although it doesn't explicitly say so. So the flower pot is in equilibrium here, and we're going to be determining its weight, and the flower pot is going to be acted upon by these two cables, AB and AC. So in our free body diagram, I'll draw that over here. We need to choose our particle of interest, or the point of interest. So we are interested in knowing something about the weight of the flower pot, and we're going to need to know about the tension in the cables for this. So looking at the picture, there's A, B, or C are potentially the points we could use. B does not directly see the weight of the flower pot. C does not either. A, where the two ropes join, the AB and BC, and the flower pot hangs from it. So A is going to be the particle that we want to model in this particle equilibrium problem. So that is going to be where I establish my origin of my coordinate system, since one was not given to us. Right, so I am going to choose a Cartesian coordinate system here. I'm going to explicitly label x positive to the right and y positive up. All right, so acting on point A, we need to model all of the forces that act at that ring where the cables and the flower pot are all joined together. So we're going to have the weight of the flower pot is going to be pulling down on that point. So we know its direction is going to be down, and we know it's going to be the weight of the flower pot, which is actually what we need to find in the end. So it's not given to us. We actually need to find W. So I'm going to call it W. That's right now an unknown. I don't know the weight of the flower pot. And I have the cable, I'll draw AC first, coming up here. Again, the tension in the rope is what is going to be pulling on point A. I don't know up front what the tension in the rope is. I'm going to call it then TAC. It must be a tension, and it goes from A to C, and it is pulling on point A. Now we are told that the maximum tension either rope can have is 50 pounds, but that does not mean that the tension in AC is 50 or necessarily that AB is 50. We're going to see when we test out which is correct. It's very, very unlikely that they will both be 50 at the same time. So at this moment, I don't know its value, so I'm going to leave it as TAC. And we were given that it makes a 30-degree angle with the positive y-axis, so I will just keep that. And then the other cable here is going to be the tension from AB. And as far as its orientation or its direction, we were given this 3-4-5 ratio triangle, so I will just stick with that. All right, so our free body diagram contains our point of interest, which is point A. I guess I'll mark it here. It contains all of the forces that act on A, the weight of the pot, the cable tension in AB and AC. It contains labels or values, in this case labels AB, TAC, TAB, and W. We don't know any of the values at the moment. And it contains the orientations or the directions. So the 30 degrees is telling us about the orientation for AC, and the ratio triangle is telling us about the orientation or the direction of TAB. And then W is purely vertical, so that's indicated here because it's on that axis. So now we have a complete free body diagram for the problem, so we can use that to drive our equation step. So we'll start with the equilibrium equations. Again, these are going to be coming directly from the free body diagram. So equation 1, I'm going to take the sum of forces that act in the x direction. The order we do these in doesn't really matter, but I'll just start with x here. I'm in static equilibrium, so I know that they must add up to 0. And now I can look over at my free body diagram and pick out just the x components of forces. and I want to make sure that I get their sign correct for this scalar equation. So W has only a y component, so nothing is in the x, so I can skip that. TAC, its x component is positive, it points to the right, so it is going to be TAC. Again, I don't know its value, and I'll use the 30 they give me. The horizontal is opposite the 30, so it's actually going to be TAC sine 30. Right, so cosine is not always going to be the x component. In this case, based on the angle that we were given, 30 degrees, the opposite of that is actually the horizontal. Now we could have said it's 60 degrees from the x-axis and gone with that, but I'll just stick with what was provided to us in the problem. And now the x component of TAB, so the horizontal component. So looking at TAB, it's going to be pointing to the left, the negative x direction. And we can use the ratio triangle there. So the horizontal component is 3 over 5 TAB. Now, if you're more comfortable using the angle instead of the ratio triangle, that's okay. It's just convenient when they provide a ratio triangle, but in real life, probably nothing is going to make a 3, 4, 5 ratio triangle angle. It's really just convenient for the mathematics of it. So this 3/5 is how much of TAB points to the left, and the sine 30 is how much of the TAC points to the right. All right, so that's our first equation, sum of forces in the x direction. All right, there's two unknowns in it, TAC, TAB, so we can't solve anything yet, so I'll move on to summing forces in the y. Again, we're in equilibrium, it's going to sum to 0. Now I need, of my three forces, all of the y components. So all of W points down, which I established as the negative y direction, so it's a negative W. And now I have the vertical components of TAB and TAC. So for TAC, it's pointing up, so it's going to be a plus TAC, and then the vertical component is the cosine 30. And for TAB, its vertical component also points up, so it's going to be plus 4/5 TAB. All right, so if we look here at equations 1 and equation 2, I have three unknowns actually, TAC, TAB, and W. I have no equation that has only one unknown in it, so I actually have three unknowns, two equations at this time. So I don't yet actually have enough equations for all of my unknowns. However, I have used up my two equilibrium equations. It's a 2D particle. I can only get two equilibrium equations out of it, sum of forces x, sum of forces y, and those are done. So I need to get at least one more equation from somewhere, and this is where I can use the information for the first time about the maximum tension that one of the cables can hold. All right, so we want the maximum weight such that neither cable fails. And again, each cable can hold at most 50 pounds. Now it is, like I said earlier, unlikely that both cables fail at the same time or both reach 50 pounds at the same time. One of them will reach it before the other. Now there's different ways we could approach this. I like to think of it as kind of testing different scenarios and seeing which one is the correct scenario. Might sometimes more time consuming, but we're considering all the possibilities. So I'm going to consider, I'll call it scenario A, where I'll say that TAB fails first. Which is to say, in scenario A, my assumption is that the tension in AB is just at that 50 pounds, and we're going to see what weight it would take to get TAB just to 50 pounds. Which means that I can now have a third equation under this assumption or under this scenario. My third equation is I'm going to enforce that TAB be 50 pounds. Now, if I look at equations 1, 2, and 3, actually I'll call this 3A so that we don't confuse it later. So equations 1 and 2 are true because they must be true. We're in static equilibrium. 3A is only true if TAB is actually the one that fails first, and that's what we are going to be testing. So equations 1, 2, 3A, I have three unknowns, and now I have three equations, so this is a solvable system. So I'm going to move on for the moment to the solve step, and then I'm actually going to come back. Right? I have 1, 2, and 3a. I want to solve those simultaneously. So I'm going to use Mathematica to solve this one. I have 3 equations. It's really not too bad to do by hand, but just as an illustration here. So I have equation 1 is going to be 0 equals. So when using Mathematica, I am naming this first equation EQ1. I use a single equal sign, and now I'm going to put in what I have written down. So 0 double equals TAC sine 30 degrees. All right, so a couple things to notice if I'm using Mathematica here. TAC is a variable name, and I put a space between it and sine. In Mathematica, all built-in functions like sine, cosine, etc. must be capitalized. So it's capital S sine, and then I use a square bracket here, 30, and I do have to specify degrees because otherwise it assumes I want it in radians. A quick way to do degrees in Mathematica, if I press escape, DEG, escape, it turns into the degree sign, and now it knows that I want to take the sine of 30 degrees and not 30 radians. Minus 3/5 space TAB. All right, so that has saved my first equation. We'll see how we use it in a second, and I'm going to put a semicolon at the end so that it doesn't print it out. All right, now I'm going to enter equation 2. I'll call it EQ2. And again, that's my second equation. My sum of forces F, or sum of forces in the Y. So 0 equals negative W, another unknown, plus TAC. I have to make sure I capitalize it, spell it the same each time so that Mathematica knows it's the same variable as I had in equation 1, cosine 30 degrees. And that's going to be plus 4 over 5 TAB. And I'll enter EQ3A. So this is TAB equals 50. Now Mathematica doesn't understand units, so we just have to know that that 50 is going to be 50 pounds. And press enter. So another thing to note that's kind of strange about Mathematica, so all 3 of these are in the same block. I have to press either the shift enter on the near the QWERTY part of the keyboard for it to run it, or I have to press the enter near the number pad and that will run it. Otherwise, if I don't do that, it just adds another space. So I want it to run it, and now it is saved into its memory. EQ1, EQ2, and EQ3A are saved. All right, so I have my 3 equations down and saved. Now I want to solve it simultaneously. Well, Mathematica has a nice solve command, so solve, again, capitalized, and then I can put in a list of the equations for it to solve. All right, so notice here, solve takes a square bracket because it's a function, and then the list of equations I want it to solve, I have to put into the curly braces. So I already knew before I went to the Mathematica step that I had 3 equations and 3 unknowns, so I already know this is a solvable system. So now if I run this solve command, it is going to solve them. I have gone ahead, I've renamed all of my unknowns to lowercase because otherwise Mathematica can get confused here. So the TAC, TAB, and W are all lowercase at this point. So now I'm going to put those into memory, and now I'm going to tell it to solve those 3 equations. So now under scenario A, we see that it says TAB is 50. Well, that has to be true because that was 3A. It solved for TAC and it solved for W. Now notice I tried to do W exactly here, so it has these radicals. I can put in the //n is one way to do it, and that's going to tell it to put everything into a decimal form. So if I solve this, TAB is 50, TAC is 60, and the weight that would cause this scenario is about 92 pounds. However, if I go back here, in scenario A, solving that, that has made TAC equal to 60 pounds. But I know that that can't be the case because I was told that the maximum tension that either cable could hold was 50 pounds. So that tells me that scenario A cannot be the scenario that's true. So what must be true, since there's only two choices, is that TAC is going to fail first, which means that my third equation will be different. 3b, I'm going to make TAC equal to 50 pounds. All right, so in scenario B, TAC fails first, so now we can solve equations 1 and 2 are still true. We are still in equilibrium here, so those stay. 3a is not going to be true when we are talking about scenario B, but 3b will be true. So now what I want to do is solve these three equations, 1, 2, and 3b, and see what my results are. Now, it should work because we already know scenario A was not correct, but we'll check what numbers we get now in Mathematica. So coming back into Mathematica, I'm going to add in my equation 3b here, and that is going to be that TAC is 50 pounds. And now I want Mathematica to solve this set of equations. So I'll keep this just so we can see it, but I'm going to make a new solve. But now the three equations I need it to solve are equation 1, equation 2, and equation 3b. Now it knows what I want to do. So now it's taking equation 1, 2, and 3b, solving them all at the same time. So it's finding that TAB is about 42 pounds. That's okay. It's below the 50-pound threshold. And the weight that causes TAC to be at its maximum value of 50 pounds, we get 76.6 pounds. So coming down here, TAB is about 41.7. That's okay. TAC is at 50, TAB is at 41.7, that's all good. And the weight that causes this, we found to be about 76.6 pounds. So the weight, 76.6 pounds. Okay, so just as a check here, again, if we put any more weight on, if it was 76.7 pounds, that is going to cause TAC to now be above the 50-pound threshold that was set. We already explored scenario A. We were theorizing that AB was the one that failed first, but for AB to just be at the verge of failure, to just be at the 50 pounds, TAC would have already failed. That's what brought us to scenario B, where now we test AC being the one that fails first. So we found for it to just be on the verge of failure, as expected, AB is below the threshold of failure, and we found the weight that just takes us to AC being the failure point. Now, in more complicated situations, we could have a lot of different modes of failure. So maybe we have 3 ropes, and one of those is going to fail first. So we might want to test what if the first one fails, the second, the third, and see which of those is a feasible situation. So like we saw here, the first scenario wasn't feasible. A rope was already past failure when AB failed. And part B, AC was just at failure, but everything else was okay. So in the end, the most weight that we can put here without either rope failing, but one rope just being at the limit, is the flower pot weighing 76.6 pounds.